Yes, something's coming. Two people, you and mix and Sanskrit Swedish. Yes. Good morning.
Recording in progress.
Okay. Jean-François Perrault. He told he cannot. Satyanadi. Good morning. Suswagatam. Yeah, and Suprabhatam also. And Vannakam also.
Good morning.
Good morning.
Oh, it works.
Well, it seems to work perfectly.
Yes. Welcome.
You will have to mute your.
Oh, I will. Oh, otherwise it's terrible. Okay. So,
Okay, now there is no echo. Okay, but then when you speak, you will have to start this. I will mute myself.
I will speak very loud and I have
Okay. Fine.
maybe introduce once more. Bonjour. Bonjour. C'est pour l'étude de métrique et de. Alors, je suis très heureux de introduire. I will say first in France. Okay.
Yeah, fine. And I need screen sharing.
Screen
So,
sharing. Okay.
If you allow me, I will.
Then I have to go to advanced options and then host all participants can.
Okay. Yeah, good. Got it.
Donc, bienvenue à la 4e conférence de Madame Amba Kulkarni. Elle est chef fondateur du département d'études de sanskrit de l'université de Hyderabad en Inde et elle est une linguiste informatique engagée à montrer la pertinence de la tradition grammaticale indienne dans le domaine de la linguistique informatique. Sous sa direction, plusieurs outils informatiques pour le sanskrit ainsi qu'un prototype de système de traduction automatique sanskrit-hindi sont développés. En 2015, elle a reçu un Vishishta Sanskrit Seva Rati Sammana, une décoration par l'Université centrale sanskrit, erstwhile Rashtriya Sanskrit Sansthan, pour sa contribution aux études et à la recherche sur le système de connaissances, le système de savoir basé sur le sanskrit. Elle a été membre de IIAS Shimla, professeur invité à l'IIT Ropa et à IIT Bhubaneswar. Récemment, elle est l'auteur d'un livre Analyse sanskrit basée sur la théorie de Shabda-Bodha, publié conjointement par l'Indian Institute of Advanced Studies, Shimla, et DK Print World. Donc, voilà, nous sommes très heureux d'avoir ici. Et donc, we are very happy to have you here in Paris at the campus Condorcet. And it's the 4th lecture, and that will be a little more on mathematical aspects of the system of metrics, like the linguistic, the meter of verse, etc. And so the floor is yours.
Yeah, thank you very much. So I'm happy to be here. This is my 4th talk and the last in the series. I thank Professor Jan Hoven and Dr. Peter for inviting me to this place. Today, unlike the previous three talks, today I will be talking on ancient Indian mathematics. Earlier talks were on linguistics. So today there is slight change in the course which I have been taking. And one of the reasons, of course, is my passion for mathematics. So when I was teaching one course in University of Hyderabad on ancient Indian mathematics, I was very much fascinated and intrigued by some of the special features that I noticed in Piṅgala Chandaśāstra. And then I thought, let me have little more study on this, and whatever I observed, those observations I am putting forth here. So the title is Recursion and Combinatorial Mathematics in Chandaśāstra. Well, this Chandaśāstra is a text that is typically used to understand the Vedas. It is called a Vedanga. Vedas are in metrical composition. So in order to understand these, specific discipline evolved, and that is the Chandaśāstra. Shastra is the science and Chandas is the meter. So discipline which discusses, studies, and put forth various observations regarding metrical analysis. So this Piṅgala Chandaśāstra, Piṅgala, some say he is brother of Pāṇini, who composed the grammar for Sanskrit. But nevertheless, whether he is brother or not, one thing that is common between the two is both of them have composed their scientific treatise following the sutra style, where the information is in very cryptic form. And both these texts, Piṅgala's text as well as Pāṇini's text, have 8 chapters in it. The Piṅgala Chandaśāstra gives exhaustive account of Sanskrit meters, and the last chapter among these 8 chapters has around 16 sutras which provide some generalizations of these meters, mathematical generalizations, and these are purely theoretical in nature. So it's something very interesting. If we look at various Indian disciplines that were evolved, they were all application oriented. And of course, in linguistics, in the language sciences, we see generalizations which were very much available to all the linguists later on. But the generalizations that are given by Piṅgala in Piṅgala Chandaśāstra, because Chandaśāstra is something which is not related to mathematics, these generalizations which Piṅgala has given, these were unfortunately not available for a long time to the scientific community or mathematicians of the West. They were discovered very late. Now, the meters in Sanskrit are classified into 3 types. One is the Akshara Chanda. Akshara is a syllable. So depending on the number of syllables, so the meter will have specific number of syllables, 30 syllables, 15 syllables, etc. This is one kind of meter. The other kind of meter is where the duration is counted. So these are called matra chanda. Matra is the duration, it's the time measurement. The syllables are classified into two types, long and short, like short E and long E, short and long. The vowels, they have short or long duration. And based on that, the syllables are classified into two types. But these matra chandas are further classified into two types. One where only the duration is counted. And so how many total matras are there? The other one where you also look at the pattern among the matras. So how many short, how many long, what is the pattern? So typically the pattern is counted as a triplet. So a triplet, there will be 8 triplets with short and long. So they are named as Yamatara Jabhanasa. So these triplets are used for specifying the patterns. These are called the Gana Vruttas. Sorry, there is a typo, Gana, it should be N and dot below it. So Piṅgala's algorithms correspond to the study of these matra vruttas, and the short and long matras, they are called Laghu and Guru. So I will be using L and G, L for short and G for the long one. This, of course, Chandaśāstra, as I said, is a discipline which is needed in order to understand Vedas. So there were further, there is a continuous tradition of studying these, and there are several authors who wrote on these metrical patterns. In 8th century, one very important text by name Vrittaratnakara was composed by Kedar Bhatta. He also discusses the same kind of algorithms which are there in the metric in Piṅgala Chandaśāstra, but there are some differences. The Kedar Bhatta has only 6 chapters, and the last chapter discusses all these algorithms which are related to combinatorial mathematics. What I have observed is, when I was teaching to students, I observed that Piṅgala's algorithms are recursive in nature, whereas Kedar Bhatta's algorithms are all iterative. So that aroused my curiosity. I looked at them in detail. Kedar Bhatta, of course, has given several more algorithms than Piṅgala. So in this talk, I would be just discussing the 2 algorithms side by side, and let us see the recursive and iterative nature of them. And there are few more observations regarding Piṅgala's algorithm. I noticed that Piṅgala uses stack also, the data structure, and this was something which was very much interesting for me. So Piṅgala, he has given he has addressed 6 problems. He has given algorithms for 6 problems. The first, of course, these names which I am referring to here, Prastara, Nashta, Uddishta, etc., these names are not used by Piṅgala. He has just given the algorithms. But later on, the commentators have given these names. So I'm using those names. The first name is Prastara. Prastara is spread. So this tells you about the arrangement of all possible permutations of N, Guru, and Laghu sequentially. So the sequential arrangement, and of course, certain order is followed when various permutations are listed. So Piṅgala gives an algorithm to write down these permutations in a specific manner. Then there is another group of sutras which discuss nashtam. Nashta is deletion or erase. So something is erased or is destroyed. So suppose these permutations are written, of course, in those days, they were using sand, and on sand they were writing these permutations. So suppose there is a breeze and some row gets erased. Then how to recover that row? This is what nashtam deals with. Then there is another algorithm which tells you about, suppose in this list of permutations, a specific permutation you pick up, what is the position of that permutation in the given list? So this is to get the rank of a given permutation in the sequence of all permutations. And then there is fourth algorithm, which says ekadvi adi laga kriya. It tells you how to compute the number of combinations with exactly R, Ls or Gs among a sequence of n LGs. So you have a sequence of LGs. There are n L and Gs. Total n of them are there. And you need to know how many among these permutations have exactly RLs or RGs. So this is something like finding NCR, the combinations of R out of N. And then the next algorithm which he mentions is related to Sankhya. Sankhya is number. And what number it deals with? It gives you the total number of permutations of N, L, and Gs. So we know that if L and G, if we consider them as binary, 0, 1, then how many permutations, total number of permutations are there with 2 bits, with 3 bits, 4 bits, etc. This is, so there is an algorithm to deal with this. And this is something very interesting where Pāṇini has used the concept of stack. This is how I understood it. Sorry, Piṅgaḻa. Piṅgaḻa has used stack, the concept of stack here. And then the final one is Advayoga. This is to compute the total possible chandas with the number of syllables ranging from 1 to n, where each syllable is either a laghu or a guru. So these are 6 algorithms which we will be looking at. So the first one, prastaraha. This is prastara is spread. And there are 4 sutras. The first one is Dvikoglau, Mishraucha, Pruthagla Mishraha, and Vasavastrikaha. These, of course, even if you ask any Sanskrit scholar what are these, they will find it difficult to tell because these are very cryptic in nature. Let us try to understand this. Dvikoglau. Dvik. Dvik is a pair. Glau, g and l, these two make a pair. So the first sutra says G and L, they make a pair. So you have, I'm writing this as a pair. And if we replace G and L by 0 and 1, we get this. Now, why I have introduced 0, 1 will be clear in the next slide. The next sutra says Mishraucha. Mishra is to mix. You can also mix. So to get all possible permutations of 2 syllables, also mix the above 1 syllable spread, but mix with what is not clear. What Piṅgala says is also mix. Mix with what? And it is the next sutra which makes it clear. It says, Pruthagla Mishraha. Pruthak is separately, Gla, G and L, that is G and L, Mishraha. So you have to mix them separately with G and L. So we had earlier GL. I first mix it with G and then I mix it with L. So I get total 4 permutations. And if I replace G with 0 and L with 1, I have here 0, 0, 1, 0, 0, 1, 1, 1, which is all possible permutations of 2 digits, or we have binary number system here. But this is different from the way we write binary numbers in modern notation. We have 0, 0, and then we should have 1, 0, not, oops, sorry. It should have been 0, 1. I think I made a mistake. It should have been 0, 1 and 1, 0 here. So what we see is this one is actually a mirror image of, I should have 0, 1 and 1, 0. There is a mirror image. It will become clear here with the 3. The next sutra says Vasavastrikaha. Vasavaha Trikaha. Trika is triplet. And it says there are Vasavaha. Well, now this is again something very interesting about the Indian mathematics. In order to denote these numbers, they use, these are called Bhuta Sankhya, Vasu. Vasu refers to a concept in Indian tradition, which represent, there are 8 of them, 8 Vasus are there. So suppose number 2 is used to be used, they will use eyes, netra, to indicate this. So why they need these objects in the real world, which are called bhuta, the things which are there in reality? They use these because they are composing these sutras in some metrical pattern. And for that, they need to satisfy certain constraints of long and short syllables. So always they cannot use the numbers 1, 2, 3. Instead, they will use these terms which indicate those numbers. These are called the Bhuta Sankhya. So here Vasu is a Bhuta Sankhya, which refers to an object which has, there are 8 Vasus, and therefore Vasu refers to 8. So this sutra says that there are 8 triplets. So, and how these 8 triplets are to be obtained? We had the earlier one, the spread for 2. We add G to it, and then we add L to it. If I replace G and L by 0, 1, I get this pattern. But in Boolean notation, we have the number 0, 0, 0, 0, 0, 1, etc. So we see that this part is mirror image of this. And the reason again for this mirror image is here in Indian notation, the numbers are written from left to right. Okay. Whereas when we have the numbers here, when we represent the numbers, we start from right and we go in the left direction. The index increases as we go in the left direction. So this is the difference. So as we have seen, there are only 4 rules. The first one says there are 2 of them, a pair. Then you mix them separately. And the last sutra says there are 8 triplets. So now where is this recursion involved? Well, it just says Mishraucha and Pruthagla Mishraha. This is giving you the recursion. And the next one is telling you, well, in the next stage you will have 8. But it does not stop us from repeating these 2 to get the 4th, 5th, and so on. And so the recursion, though, is not explicitly mentioned, implicitly it is there, because naturally there will be a question by a student how to get the quadruplets. So Mishraucha, you just mix. And how to mix? Add G and L separately. That's it.
But maybe you should say that there is more information in the statement because it's a dual ending. And
Yeah.
the plural ending, which is different, like always plural, dual ending. So it's explicitly only 2,
Yeah.
and then it is plural.
Oh, Pruthagla Mishraha.
From there on, it is plural.
Yes.
More
Yeah.
than 2.
Right.
But their plural means not the same as our plural.
Yeah.
It is
Right.
not 1, not 2, but more.
Yeah. Yeah. Good point. Okay. So, so now what we had was, in the beginning we had this GL, which is a 2 by 1 matrix. Let me call it as A1. Then I got A2, which is a 4 by 2 matrix, by composing it in this way. So I have A21, and to this I add this 0 and 1. 0 stands for all zeros and 1 stands for all ones. Then A3, which is a 8 by 3 matrix, can be written in this way, which is composed, which is derived from composition of A4, 2 and 0 and 1 matrices. So in general, we have this, which is what this Pruthagla Mishraha means. So Mishraucha and Pruthagla Mishraha, they correspond to this. Okay. Now let us see how Kedar Bhatta gives this algorithm. Kedar Bhatta, as I said, was in approximately in 8th century AD. And by that time, of course, these studies had taken a different direction. Even in the case of grammar, if we see, we had Siddhanta Kaumudi, where the arrangement of sutras was totally different than the sutras, the arrangement in Pāṇini's Ashtadhyayi. Same thing has happened here. So there was a kind of more simplification, I would say. More emphasis was on teaching in a simple manner. Now, why I'm saying this will be clear from these shlokas. The shloka is like this: Pade sarva gurau adyat laghunyasya nyasya guroh adha yatha upari tatha shesham bhuyah kuryat amum vidhim une dadyat gurun eva yavat sarve laghu bhavet prastaraha ayam samakhyatah chando vichiti vedibhihi. So Pade sarva gurau, in the beginning, in a line, all are gurus, all are G's in the beginning. Lagunyasya guroho adaha. place a laghu L below the first G of the previous line. And then yatha upari tatha shesham. Copy the remaining right part as in the above line. Bhuyah kuryat amum vidhim. You do this, repeat this process several times. Bhuyah. Une dadyat gurun eva. Guru is G. Dadyat, give or place. Place G's in all the remaining places. Those are the places to the left because we have started from the right. For right, already a rule is given. So to the left, whatever is remaining, you place G. Yavat sarve laghuhu bhavet. Till all of them become laghu. Prastaraha ayam samakhyataha. This process is known as prastara. Samakhyataha is known as, ayam is this process, chando vichiti vedibhihi, by the experts in the chandas. So this is the algorithm, and now let me explain this with an example. So it says, in a line, first all are gurus. So start with all G's. I am explaining with prastara or spread for three bits. Then the rule says that place L below the first G. First G is this, place L, and copy the remaining bits, right bits, from the above line. Repeat the same thing. Now we have LGG. Below the first G, write down L, copy this as it is, and to the left add G. So now we have GLG. Below this G, we write L below the first G, and we copy this LG as it is. Now we have LLG. Below the first G, we write L, and the left is filled with G's. Again, below this first G, we write L. This is copied as it is. Now we have LGL. Below the first G, we write L. We copy this as it is, and the left is filled with G. The first G is replaced by L. Remaining part is copied. And since now we have got all else, we stop. So the algorithm is iterative in nature. Once we know the previous stage, we can go to the next with this. And in order to get this spread, unlike in the previous algorithm, in Piṅgala's algorithm, to get this 8x3 matrix, we need to have the spread for 2, and then we added G and L to it. But here it's not the case. We are directly starting with 3 or 4, etc. So for students, this is something which is easier. They can write down the spread prastara for 4 bits or 5 bits and so on very quickly using this algorithm. If the recursion is to be used, they have to start with first, then second, then 3, 4, 5, and so on. Here, you need not go to the previous ones. Directly, you can write this. Okay. Now the next one. Now this algorithm for nashtam is something is erased. Now when something is erased, for Kedar it is very easy. Suppose you have this and one row is erased. Since you know the algorithm where how to go from the previous to the next one, you can always retrieve it very easily. But this is not the case with Piṅgala. In the case of Piṅgala, we do not know how to go from the previous row to the next row. So he had to give a separate algorithm, and it says la ardhe sa eke g. La ardhe. Ardha is half. If the given number can be halved, then write L. If it is divisible by 2, then write L. Sa AK. If it can be halved by after adding 1, then write G. This is the algorithm. Now, let us see. So we have the number 5. Only after adding 1, we can halve it. So we write G. But then how to proceed further? So now, since the human who is, the instruction says if it can be halved by adding 1, that means mentally you have already halved it. Now, since you have halved it, whatever number you have got, with that you continue. So now you have 3. Again, this is, you need to add 1 and then it can be halved. And then you write G. And see, you are writing these from left to right. And now you have 2. This is divisible by 2. We get 1 and we write L. How do we know? We have to stop here. The 2 statements that are given here, they don't tell us anything about it, that you stop this recursion. Even recursion is not explicitly mentioned, but we need to infer this recursion. So now why do we stop here? Well, I can continue with L. After this, we have 1. So we will have 1 plus 1 by 2, which is 1. Write G, and so on. So after this, we will have all G, etc. So actually, these G stands for 0, as I mentioned. So it is not carrying any information as such. It's not carrying any value as such. So you can continue writing G's. You stop whenever you want to. So if you want a representation as 5 digits or 6 digits or 7 digits, you continue till that. That's it. But as I said, the G's will not carry any value. These are just 0, 0, zeros appended. That's it. So we can write this algorithm as to get, now we are writing this in terms of GL binary. So I have named the algorithm as get binary. Get binary says you print L if n is even, and then calculate, call this get binary with n by 2. And if n is odd, print G and you call this with n plus 1 by 2. And this is the terminating condition. If n is equal to 1, you stop. Well, and this is the normal way of getting binary equivalent for a decimal number. So we have this algorithm by Piṅgala, which gives you decimal to binary conversion. Now here, I need to point out 2 things. Now this GGL will be 0, 0, 1. I said G is 0 and L is 1. So it will be 0, 0, 1. So this 5 will be 0, 0, 1. If I take a mirror image, it will be 1, 0, 0. But we know that 1, 0, 0 in binary is 4 and not 5. So why this difference? 5 will be 1, 0, 1. So there is something wrong. And what is this wrong? Why this is the, what is the problem? So if we look at these again, this GGG, Piṅgala is calling it 1, whereas 0, 0, 0, we say it is 0, its value is 0. So the counting here is done starting with 1. So you have 1 to 8, not 0 to 7. And that's why we have here 100 is equivalent to 4 in binary, but for Piṅgala, GGL is 5. So these are the two major differences which were observed by Newton. The numbers are written with the higher place value digits to the right of lower place value digits in a reverse way, and the counting starts with 1. So that's why we have to take this mirror and add 1 to get the equivalent in binary. Okay, the next one is to obtain, this is the third algorithm, to obtain the position of the uddishta, that is the desired row, in a given spread without counting its position from the top. So suppose the spread is given. So suppose you are given this GG, given this, just a minute. Yeah. If you are given this GGL, then what is its position in the spread? This is what now we want to find. In the earlier, we know which row is erased. Say, for example, 5th row is erased. What is the content of that row? What is the permutation there? That what is the pattern that we have found? Now the reverse problem, if GGL is given, then how do we know that it is the 5th row? So the algorithm for this has been given both by Piṅgala as well as Kedarnath. So this is the inverse operation of erase. The sutras are pratiloma gunam dvihi la adyam tataha gi ekam jayat. Pratiloma gunam, meaning of this is in the reverse order. Dvihi la adyam. La adyam, starting from the first la, first L. Dvihi is multiplied by 2. This is first sutra. And the second says, tataha, from that, gi ekam, gi is G. So if the syllable is G, if it is Guru, if it is G, then from that, subtract jahyat, ekam, remove 1 from that. Now, if the syllable is G, remove 1 from it, but after multiplying it by 2. This dvihi is to be considered in the second sutra also. And this is the style which is there for compactness. This method of borrowing the words from the previous, this is called anuvrutti. And we find this in the sutra style, even in Pāṇini and in Piṅgala also. So we find this method of borrowing the words from the previous sutras in order to make it complete sentence. So, okay, so this says that in the reverse order, starting from the first lagu, you multiply by 2. Multiply what? What is the starting number? That is not mentioned. So we assume that we start with 1, the multiplicative identity. So let us see this GLG. Suppose GLG is the pattern. Starting from the first L from the right, this is L. We start with 1, multiply by 2. Then we go to the next one, next digit. This is G. So we multiply 2 and then subtract 1. So this GLG corresponds to 3, or it is in the third position in the spread of 3 numbers. So GLG, we can see if it is, yes, it is in the third position. Okay. Okay. Well, this algorithm I have translated into modern notation. We can skip this. Now let us see what Kedar has to say on this. Now Kedar Bhatta says, Uddishtam dvigunan adyan upari ankan samalikhet lagustha etu tatra ankan taihi sa ekaihi mishraihi bhavet. Uddishtam dvigunan adyan. Uddishtam. Uddishta is something that is desired. Dvigunan. You need to double it. Adyan. Starting from the first. Upari ankan samalikhet. Upari on the top. Ankan, the numbers. Samalikhet. Write down these. Lagustha etu tatra. Lagustha, sorry, there is a typo. Lagustha etu tatra. Those which are on the top of Laghu, tatra ankan taihi sa ekaihi. With that, add 1. Mishritaihi is add 1, and whatever you get is corresponding number. So this is something, there are some typos here, I'm sorry. So this says that in order to get the corresponding number for the given Laghu Guru LG combination, you start from the first and write the numbers by doubling each time. But when you are doubling, what is the starting number? That is again not mentioned. So we start with 1. So suppose you have GLL, we start with 1. Then we write on the next 2, on the next twice this, that is 4. And then we add all the numbers that are on the top of L, that is 2, 4, 2 and 4. And to this we add 1 and we get the position of GLL in the matrix. So I will repeat this. To get the row number corresponding to the given LG combination, Uddishtam, Dvigunan Adyan Upari Ankan Samalikhet. You go on writing Samalikhet, you go on writing them. Upari, on the top. You need to write them. Starting from the first, of course, Adyan we can consider starting from the first. That is, you have GLL, from left to right you are going. Starting from the first, you go on writing the numbers which are double the previous number. So this is what we did. GLL is the pattern. We started. Now, which number we need to start with? That is not mentioned. We start with 1. And then multiplied by 2 and then multiplied by 2 again, we get 1 to 4. The next line says, Laghustha etu tatra. Those which are on the Laghu, on L, those numbers, add 1 to them and mix, mishritaihi. mix all these with 1. So the ones which are on L are 2 and 4, and to this we add 1 and we get 7. And GLL was indeed the 7th row in this list of 8s. So this was the algorithm by Kedar. Now this is something which is a bit controversial. As far as Kedar algorithm is concerned, I don't know. Yeah, here is the Kedar's algorithm. Kedar's algorithm is very clear, Kedar Bhatta's algorithm, but the Piṅgala's algorithm is something which is controversial in its interpretation. First, I will explain Kedar Bhatt's, which is not controversial. So it says, Varnan Vrutta Bhavansa Ekan Autarardhyayataha Sthitan Ekadi Kramataha Cha Etan Upari Upari Nikshipet Upantyato Nivartate Tyajet Ekaikam Urdhva Adhataha Urdhvataha Upari Adyad Guroho Evam Ekadvi Adi Lagakriya. Now what are they talking about? Ekadvi Adi. Eka is 1, Dvi is 2, Adi is etc. 1, 2, etc. LG process. So 1L, 2Ls, 3Ls, and so on. So how many 1Ls, how many permutations are there with 1L? How many of them are there with 2Ls? How many with 3Ls, and so on? This is what they are calculating here. So the meaning of this is whatever is the given number of syllables. So suppose it is 3 bits or 4 bits, whatever is the number, let us take 3. Write those many ones from left to right as well as top to bottom. Uttara adhataha. Then starting from 1, Ekadi Kramataha, add the numbers to the top row, Upari Upari, and continue this process leaving the last number. The last numbers in the first column stands for all G's. The last number in the second column stands for 1 L and remaining G's, and so on. So what they are saying is, suppose you are talking about 6 bits, then write these 6 times 1s from left to right and from top to bottom. Then add this 1 to this one and write the sum here. Add 2 to 1, write the sum here. Continue this process till the last but one, Upantya. Then again continue this 1 plus 2, 3, 3 plus 3, 6, 4, 10, and so on. And you stop at the last but one. And then from the right side, this tells you how many rows are there with all G's, 1 G and remaining L's, then 2 G's and remaining L's, and so on, and here all L's. So we have 1, 6, 15, 20, 15, 6, 1, which is nothing but the binomial coefficients. This algorithm was very clear. You can make this from this algorithm. This is called Meru because it's like a hill. If I slant it and put it this way by 45 degrees. But the algorithm given by Piṅgala is very cryptic. And typically, this Meru, the Pascal's triangle, when the Indians talk about it, they attribute it to Piṅgala. The Piṅgala's algorithm says pare purnam iti. Pare means the other one, or something which is on the other side, far away kind of thing. Purnam is complete. And so literally it means completed using the two far ends, pare, which is in dual. So using the two far ends, complete it. Now what are these two far ends? Nothing is clear. And then it is the commentary which tells you how to construct this. But then there are various criticisms on it. People, of course, interpret it in a different way also. This pare purnam, they try to borrow some words from the previous sutra and try to interpret. There are various interpretations. And somehow I was not satisfied with all these interpretations. Then there is a Gurukula where these texts are taught to the students. So I went to the Gurukula and I told the Acharya, the Guru, the teacher there, that I want to understand these sutras and I want to know how you teach them. So he said, well, we do it this way. We have these ones. Now, from where he gets these ones, I do not know. He says we have these two sides and we complete them. How do you complete them? He said, I add 1 and 1 to get 2. I add 1 and 2 to get 3, 1, 3 to get 4, and so on. So like this, I complete and so on. And I get these 1, 4, 6, 4, 1, 1, 5, 10, 5, 1, etc., which is the Pascal's triangle. Well, but still the things are not very clear. How do we get this? As I said, the Piṅgala's text is in cryptic form. It is in sutra form. So from that sutra, though for the earlier sutras, we could get the information, the algorithm. Here it is so cryptic that I could not get it just from the words. But of course, various scholars have tried to interpret it using various ways. And the claim is that these two sutras give you the Meru construction. Okay, now the fourth one is Sankhya. Sankhya actually means number. But this number is number of possible permutations of n GLs. So Kedar Bhatta uses the results of this previous operation. Two operations we have seen. One is Uddishtam and the other one Ekadvyadilaga Kriya. He uses these two operations and he arrives at interesting mathematical formulae. Whereas Piṅgala gives a totally independent algorithm, and this algorithm has intrigued me a lot because in order to understand that algorithm, unless you have the concept of stack in your mind, the data structure, you cannot do this. So let us see these one by one. The first one is Kedar Bhatta's algorithm or the shloka. Laga kriyanka sandohe bhavet sankhya vimishrite uddishtanka samaharaha sa eko va janayet imam. This va means optionally. So he is giving two algorithms. Laga kriya anka sandohe. Whatever numbers we have obtained in the previous laga process, that is triangle construction. When you add them, vimishrite bhavet sankhya, it leads to a number, this sankhya, which is the total number of permutations. Or this can be generated, imam janayet. You may generate this by adding 1 to the addition, to the sum of the numbers that you used in the uddishta. There was one process called uddishta, where we wanted to know the desired number of the corresponding row. There we had written 1, 2, 4, etc. Those are the uddishta. So you can add them and add 1 to it, you will get this number. So if it is, say, 6 bit permutations we want of 6 GLs, how many will be there? For 6, we had 1, 6, 15, 20, 15, 6, 1 in this triangle. For corresponding to the 6th row, we have 1, 5, 10, 1, 6, 15, 20, 15, 6, 1. So these are the numbers. When we add them, we get 64. And the uddishta numbers, uddishta we had seen here, uddishta of Kedar, where we were writing these numbers 1, 2, 4, and so on. If it is 6, then we will have the next one 8, 16, 32, and so on. So the numbers here are 1, 2, 4, 8, 16, 32. These are the 6 numbers. Add 1 to their sum and we get 64. So essentially, Kedar vector seems to be aware of these two well-known formulae, sigma NCR from 0 to n is 2 raised to n, or sigma 2 raised to I from 0 to n minus 1 plus 1 is 2 raised to n. Okay, this was in 8th century. Now let us come to Piṅgala, which is very interesting algorithm. It says dvihi ardhe rupe shunyam dvihi shunne tavat arthe ardhe tad gunitam. The word shunya, which stands for 0, is used here. And this is again the first instance in the mathematical text which I have come across where 0 is used. But this 0 in this particular context does not represent a number, as I will explain. It just represents a symbol, not a number 0. Okay, I will come to that. So, dvihi ardhe. Ardhe is if the number is divisible by 2, if it can be halved. Dvihi, write 2. This divided by 2 is implicit because already mentally we have done it. So it is assumed that you have already divided it by 2. Rupe, if subtracting 1 from it makes it divisible by 2, then write 0. And then it says, dvihi shunne, if the answer was 2, if the answer were 0, then dvihi, multiply by 2, and tavad ardhe tad gunitam, if it were divisible by 2, tad gunitam means by itself, tavat tad gunitam. So tad gunitam, you multiply, and tavat by itself. So what is this algorithm? Let us take one example and see. Suppose 8 is the number. What Piṅgala wants to do is calculate 2 raised to 8. So he says, if it is divisible by 2, divide it by 2 and write 2 here. Again, 4 is divisible by 2, divide it by 2 and write 2. 2 is divisible by 2, divide it by 2 and write 2. 1 is not divisible by 2, subtract 1, so 0, and write 0. Now, since we have obtained 0, no more operations, we stop here. Now, we start with the second column, this 2 to 0, but from bottom to top. So I have written them as 0, 2, 2, 2. So this is the stack which I'm talking about. And now the next 2 sutras. See, the first 2 sutras, dvihi ardhe rupe shunyam. They tell you write 2 or 0, which we have done. Now the next 2 sutras, dvihi shunye tavad arthe tadgunitam. So if it is 0, dvihi shunye, if it is 0, multiply by 2. Multiply what? Again, we take 1, multiply it by 2. If the answer were 2, then multiply with itself, multiply by itself. So 2 into 2 is 4. Again, it is 2, so 4 into 4, and again 2, 16 into 16, we get 256. So this is interesting from 2 points. First one, we need to apply these 2 sutras first, get intermediate result, and then apply the next 2 sutras on that intermediate result. That intermediate result needs to be kept in memory. Okay. And then we need to unstack this. And this shunyam, rupe shunyam, as you have noticed, this whatever shunya you are writing, 0 you are writing here, this 0 actually is just a symbol. These 0 and 2s are just symbols. This 0 does not mean 0. It just says that, okay, he could have used instead of 0, A, B, whatever, anything. It just says, he is saying dvihi ardhe rupe shunyam. In the case of, if it is can be halved, then dvihi, just 2, that's it. Instead of dvihi, he could have used some other word. Rupe shunyam, he could have used something else, because actually he is not making use of the values of these 2 and 0 anywhere in these calculations. When it is 0, he is saying multiply by 2. If it is 2, multiply by. Okay. So essentially the algorithm is like this. To calculate the power of n, 2 to the power n, if n is even, you calculate the power of 2 to the power n by 2 and square it. If n is odd, you calculate the 2 to the power n minus 1 and multiply it by 2. And when n is 0, then its value is 1. So these 2 and 0s which were here, these were just like tokens, some intermediary result, which carry the information for the next action. Okay. And the results after each call of the function are stacked. So it is still unclear to me which part of the sutra codes information about stack. This sutra, the first two say you carry out this information. The next sutra says you do this, but you need to do this on the result of the previous two. This is not clear. And also, we need to start with one, etc. Those are some observations which I have observed in each of these algorithms. Whenever there are multiplications, they start with one, but it is not explicitly mentioned. So this is again a recursive algorithm with complexity order of log n. And Knuth has referred to this algorithm as a binary method. Actually, it was Knuth's reference to this algorithm which made me to look at Piṅgala.
He mentioned Piṅgala.
Yes, he has mentioned Piṅgala.
Because Van Noten earlier also wrote article on it.
Yeah, but Knuth is much before that.
Okay. Oh.
Knuth has written this much before. This is, I don't remember, but must be in 80. Do you have any idea, Knuth, when he wrote? This is on numerical, semi-numerical algorithms, I think second volume of Knuth.
It's in his numerical recipes, actually. The volume is called numerical recipes, I guess, something like that. Or numerical
numerical methods. Yeah, it's called semi-numerical methods.
And he seems to be aware of Indian mathematics, actually.
Yeah,
he makes some comment about that.
Yes, yes. And I think Colebrook has this. Okay. It is much before this. So from Colebrook, he might have.
And also Albrecht Weber had a long paper on this. And,
will you please repeat? I missed it.
Albrecht Weber.
Yeah, Weber. Actually, it is Weber's paper which I was referring to when Weber is actually that Parepurnam, the Pascal's triangle. Right. There, Weber is alluding to borrowing some words from the previous one and then interpret the sutra so that you get this. But it's not clear how you get that Pascal's triangle from it. And I wanted to refer to Weber's paper. Thank you very much. I had forgotten the name of the author at that point in time. Then there is another thing for Adva Yoga. The sutra is Dvihi Dvihi Unam Tad Antanam. Adva Yoga is to get the sum of all the chandas with number of syllables less than or equal to n. So how many meters are there with syllables less than or equal to 5? So meters with one syllable, with two syllables, with 3, 4, and 5 together, what is the number? So it says, Dvihi Dvihi Unam Tad Antanam. Tad Antanam. That is, multiply the last one by 2 and then subtract 2. So the last one, so suppose you want up to 5. So 2 raised to 5, whatever Sankhya was there, multiplied by 2 and subtract 2, you will get the sum 1 plus 2 plus 3 plus 4, 1 plus 2 plus 4 plus 8 plus 16. So essentially they are saying, if you want the sum of this 2 raised to I from 1 to n, you start with this 2 raised to n multiplied by 2 and subtract 2 and you will get the number. These are the algorithms which are given in Piṅgala. In Kedar Bhatta's 6th chapter, actually in the commentary, there is a Narayani commentary by somebody by name Narayani. In that commentary, there is very interesting algorithm. Again, I could not get the original text from Kedar Bhatta, but in this commentary, there is one shloka which tells you in the spread of these n LGs, suppose I want to know the positions of all those patterns where exactly R G's are there. Okay, so suppose I have a spread with 5 LGs, and I want to know in that spread which are the rows where exactly 3 G's are there, 3G and 2 L's. So this algorithm gives you those positions. The algorithm goes like this. Eko dvantah chatvarah tatah ashtau iti vardhanam. Ekah dvau atha chatvarah tatah ashtau iti vardhanam. So the numbers are to be increased as 1, 2, 4, 8, and so on. Purvam parena, the previous with the latter, sanyojya, adding them together, tad adhau lekhayet buddha. So adding the previous one to the latter should be written below it. Antimau adhim naiv. Antima avadhim naiva langayet atra kutrachit. Antima avadhim, whatever is the last number, the limit, don't cross it. Na eva langayet, should not be crossed anywhere. Ekatra likhitam pradnyah punah anyatra no likhet. Once you have written some number, don't write it somewhere else. So this algorithm describes a structure which is in the shape of a flag, the earlier Indian flags. I will show you that shape, such that the jth column has positions of the rows in the spread with JLs. Okay. So let me directly go to the algorithm. So suppose we want to know the positions of 1L, 2Ls, 3Ls, etc. in the spread of 5 bits. So we write first these 5 numbers, 1, 2, 4, 8, 16, 32. Okay. Then below these 2, we write 1 plus 2 is 3, 1 plus 4 is 5, 1 plus 8, 9, and 1 plus 16, 17. So these 2, 3, 5, 9, 17, they tell me that in these positions, there will be 1 L only, and all others are G's. Okay. No, sorry. Yes, one L in these positions. Then how to get this column? Now we started with 1. Now you start with 2. 2 plus 4 is 6. 2 plus 8 is 10. 2 plus 16 is 18. We don't write 2 plus 32 because you are crossing the limit. You should not cross the limit. Okay. So only up to 18. This is for 2. But there are other numbers. So then you add 3. 3 plus 4 is 7. 3 plus 8 is 11. 3 plus 16 is 19. We don't add 3 plus 32. Now we have 5 plus 4. But 9 already we have written here. If you have written a number, you should not write it again. So we don't write 9. 5 plus 8 is 13. And then 5 plus 16 is 21. 9 plus 4, 13, already written. 9 plus 8, 17 is here. 9 plus 16, 25 is written here. 17 plus 4, 21 is here. 17 plus 8, 25 is already here. 17 plus 16, it crosses 32. So we don't write. So these are the positions where you will find exactly 2 L's in the expansion. And we repeat this process. So how do we get 12? This is 4 plus 8, 12, 4 plus 16, 20, then 6 plus 8, 14, 6 plus 16, 22, 10 plus 8, 18, but it is already written here, we skip it. 10 plus 16, 26, then 18 plus 8, already we have written. 18 plus 16 crosses 32, 7 plus 8 is 15, 7 plus 16 is 23, and then we have 11 plus 8, 19 already written. 11 plus 16 is 27, and then similarly we get 29, 13 plus 16, and then this one. This shape is in the form of a flag. This was the kind of flag which we used to have. If you look at Mahabharata or Ramayana pictures, where the kings were carrying these flags, they were of this type. You rotate it, turn it by 90 degrees, and you will have the spread like this. Okay. And therefore, this is a flag, Pataka Prastara. And you have here 1, here 5 numbers, here 10 each, 5 and 1. So you get again these binomial coefficients. Okay. So let me conclude now. So Piṅgala used recursion to describe the combinatorial algorithms. All these algorithms are tail recursive, so they don't need any stack again for calculations, etc. The terminating condition for this recursion is not always explicit, as I have pointed out. The initial condition or terminating condition for the recursion, whether to start with, which number to start with when it is multiplication and so on. Then use of stack to store the intermediate data structure. This was something which was something fascinating for me. And Kedar Bhatta's algorithms were all iterative in nature. Recursion, we know, is good for modeling, abstraction, and so on. And iteration is good for teaching or practicing. So maybe there was a change in the trend in Indian teaching tradition also, where there was a period where more emphasis was on modeling, abstraction, that we see in Pāṇini also. Whereas later on, when there was a spread and students were finding it difficult to visualize this abstraction or understand this abstraction, and when they needed some practice naturally, they might have gone for the iterative algorithms. Okay, so that's what I wanted to share with all of you. Thank you, and I welcome questions.
Merci beaucoup, thank you. Est-ce qu'il y a des questions? Questions, remarks? I think this article of Van Noten, Barend Van Noten, I think it was 92 in the Journal of Indian Philosophy. That's very useful also in addition to, because it is very directly coming to. I'll try to find the reference. But,
I think I have reference of Van Newton.
Refers to Leibniz, I think so, and to Chinese combinatorial patterns with these trigrams, and it so happens that the trigrams are also on the GED doors. If you walk through this morning, you saw maybe these 3 grams. Maybe you noticed that they are used as a decorative. There are 8 3 grams in the I Ching in this in the Chinese philosophy book, Oracle philosophy. But Van Noten, he refers to all that, but he focuses on chandas. I'm trying to find the reference, but and in the meantime there might be other questions because he explains it very. Van Noten, Journal of Indian Philosophy. That was in binary numbers in Indian antiquity.
Yeah, this is by Van Newton.
Van Noten, well, Van Noten, there's a Dutch name originally, but he is fully American, of course. 93 it was. So if any student or wants to know more, I think this will also be useful. But Knut is very mathematical and very.
Yes, Knut is a very old one. Yeah,
and a very brief. He knew a lot, but he doesn't explain clearly about the Indian system. A little bit he mentions, but also this way to remember this short and long.
Yamatara Jabhana Salaga. Yeah, this is again, this is De Broglie sequence.
So it's remarkable that the Indians, they were very close to these binary numbers, but didn't do much more beyond metrics.
Yeah.
They didn't build a computer, means they had all knowledge of the binary numbers. But apart from not building a computer, also in
fact, I don't know whether these mathematicians had, of course, those who have studied Vedas, they had exposure to these, but otherwise, well, the combinatorial mathematics, Bhaskaracharya, of course, knew about it. Bhaskaracharya has given a different algorithm for.
Bhaskara is the real great mathematician.
Yeah, Bhaskaracharya is, I think I'm referring to second, who wrote this Lilavati, who was, I think he was from 5th century, if I'm correct. I don't remember, very bad at I don't remember maybe 5th or 6th century. He wrote this book by name Lilavati, which has arithmetic, mensuration, and geometry. It deals with various of these. And then, of course, he has a lot of contribution in the lunisolar calendar and other things related to it. There is one work by him is Surya Siddhanta, so which deals with again the solar system. And so he has given a different recursive formula for this binomial coefficients, which I refer to NCR, where we have 1, 6, the row in the Pascal's triangle. To calculate these, Bhaskaracharya is given some other algorithm. So, yes, you are saying something, Satyanath? I think I should.
Bhaskaracharya would be the second Bhaskaracharya would be in the 12th century, of course. The one small thing about the general idea of recursion being replaced by iteration. I mean, they are both, but there is one place where there is tail recursion, both kinds of recursion, which is what is called known as the Kutakara. Kutakara is the method for solving congruence problems. Unfortunately, it is called Chinese remainder theorem in modern mathematics for reasons that are wrong, but that's not the point here. And here you have what is called there is a sequence of quotients, and then there is a way to generate them, and then to you know,
Yes.
to work your way upwards, and you
Yeah.
work your way upwards really in a recursive fashion.
Yeah.
And there is one thing which is very strange, which I pointed out in my review of the Karana Paddhati by allso and his colleagues, which is that there is another algorithm that starts with the same sequence of quotients, but start from the top.
Okay.
And so what the author of Karana Paddhati Somayaji noticed is that if you work the same algorithm recursively, but from the top rather than from the bottom, you get the same numbers.
Oh, so instead of that means they are using stack in one, and the other one is treating it as a queue and then calculating.
I mean, both cases you have a queue because you have a list of, I mean, what the method is this: you have two numbers and you divide the greater one by the smaller one, and you replace the greater one by the remainder.
Okay.
And then you store the quotient in the queue.
Okay.
And so you iterate until it's no longer possible. So assume that there are no common factors, it will end at 1. And so you have a list of quotients, and then the numbers have been destroyed. So there is the standard algorithm that you already find in Aryabhata, is that if you start from the bottom, and there is a simple way to go up, and then you can recover the original two numbers. And if you start with the remainder problem with given remainders, then you put the remainders instead of 0 and 1, and you get the solution. That's the same algorithm gives you the solution of the problem. Now, what Puddhamana Somayaji noticed is that if you take it as an abstract process, so starting from a queue and then putting 1 and 0 at the bottom, you get a certain number. And then if you start from the top and reverse the queue, you get the same number.
I see.
And the point is that when you do that, it enables you to recursively obtain the list of higher and higher or better and better approximations of the fraction a over b corresponding to the two numbers you divide from one another by one another. And so he uses it to get approximation for astronomical periods that are quotients of numbers with 7 or 8 digits each.
So
and
this is
yes?
just a minute. This is the Kuttaka method you are referring to, right?
Yeah, the first part, I mean, the regular part where you start from the bottom is the, I mean, Brahmagupta called this Kara, and then he used to call Kuttaga the multiplier that is the x and one of the unknowns in the problem. And then later authors tend to use there are three terms: Kuttagara or Kutigara for Mahavira, and Kuttaga and Kutta. And the two solutions are sometimes called the upper Kutta and the lower Kutta. That's also so. I'm using the older terminology.
Okay.
Now too, seems to be Kuttaga seems to be the older one. And as I pointed out as well, if you the etymology seems to go back to the idea of division. And so what is the new point that was found in the Karana Paddhati is that you can make the same algorithm starting from the top, and one of the numbers is the same. And so this thing has been interpreted in terms of, by the editors, by relations in terms of continued fractions, but there are no continued fractions in Indian mathematics. There are lists of complex fractions. There are lots of, there are, and how you reduce them to the standard form, that there is no continued fraction. So what there is this thing, and this basic theorem. I don't know whether it was older than Puddhamana Somayaji, could be, but this is the key to relating this to continued fraction. So that it means that the idea of recursion is something that you do find, and it is important in Indian mathematics. So is one easier than the other? It's not clear. And the iterative methods also for solution of the equation is something also that people have used very creatively. So I mean, one needs to look at many examples to see what the relative. But it's interesting to try to understand which is which.
Yeah, but but recursion definitely requires this stack. The stack is needed in order to.
Right.
So from, of course, well, I will not go in these details from computational point of view.
No, but I mean, you see it, I mean, in the Indian text, there are two kinds of methods. Those where you actually keep track of results, like I said, so you really have a queue. And those where you erase intermediate results. So there you only have a local stack. It's like, you know, as you do in your just, I don't know whether you played with calculators in reverse Polish notation. So for instance, you take the HP 41C, if you have played with that, it has 4 stacks. So there are 4 elements in the stack, and if you add a 5th number, then the 4th one gets erased. There's something like that. So there are a few cases, and so there are some problems where you actually, like in the division, you erase intermediate remainders, and therefore you don't have them. So therefore you need to have a local algorithm that only works. But if you keep a record of a queue, and then you have something else, and you have an actual, you have a longer list. And if you have kept a record of that list, then the algorithm becomes different. So there is a direct relation with the way the things are actually written. So there's a historical, it's not just from a modern point of view. There is this difference is relevant from the Indian point of view.
Well, just two comments. One is kutta. This kutta is beating. So you are beating it in smaller parts.
That's what people have said later, but what I pointed out in another paper, if you look at the Dhatu Partha, it doesn't say that. It says Cheda Batsnayor, and that's it. And Cheda actually is, of course, very relevant to what's going on. And the idea of Kutta is not appropriate for explaining the examples in Mahavira's Ganita-Sāra. If you look at the Ganita-Sāra, there is a whole section on Kutigaha. It's not about multiplication. I mean, they're all about distribution problems. You cannot explain it by saying that the idea of a product, or saying that the kutta is the multiplier and it's a variant of hatta and things like that. But it is so it's not very clear. I mean, it's true. What you're saying is perfectly true after Bhaskara, and there are many people who say that, but it's not entirely clear that it's, like I said, it's not consistent with the older dictionaries.
Okay.
So that's very general. So
very
let's see
kutta.
what Pāṇini says.
No, but kutta I could not find in the Dhatu Partha. Kuttane is there.
No, kutta chedana basnayor, I think. Well, you should look in my paper on Brahmagupta's Kuttaga in Ganita Varadi that's appeared in the last issue, I think.
Yeah, Kutta Pratapane is
10
there.
something.
Kutta Pratapane.
I quoted it from Pāṇini's text edited by Boetlink. So if you look at Boetlink, because he gives also the Dhatu Partha in addition.
Okay.
It's also found in other places.
Yeah, but I could not get kutta somehow. Okay. Maybe kut. Oops. Well, kutta Kautilya is there. Kutta Pratapane is there, but I don't find kutta Chedane. I need to see.
Chedane basnayor. Well,
no,
let me try to get my paper, and then I can give you the exact reference.
Chedane.
It's in the 10th section in
Okay, Rajgana. Okay.
Reprints.
I could not get this. Yes, Chedane is there. Kutta. Okay, I got it.
Okay.
Chedane, Bhartsane.
Right.
Yeah. Okay. Chedane and Bhartsane. Okay. So Chedane, Cheda is to split.
And it also means to divide, and it's a very common term for division.
Yeah, right. So it is, you are dividing it into smaller and smaller parts.
Actually, it's a division in the mathematical sense. I mean, this you don't need to this detour about it. It's not about. I mean, when Colebrooke popularized the translation by pulverizer, it's not pulverizing. It's not the churner. I mean, the powder is churner. It's not that. The decomposition rather than pulverization, if you want.
Okay. Okay. Yeah. Thank you. Any other
questions or remarks or not so well.
I'm not a mathematician at all, but it's a question of the word shunya. I mean, like, and it makes me think about high school mathematics. I haven't done mathematics since. Like, if it is like symbol, are we supposed to like treat it like something like an X, or like, because if it has no, like you said, it has no value. If it's a symbol, are we supposed to treat it like an X? I mean, like, did the
yes, that's what I said. See, here in this particular situation, in this context, this word shunya and dvi, he has used two. He could have used A, B, whatever, X, Y, anything. It would not have made any change. The final result would have been the same. So from that point of view, I'm just saying that it is just some variable, some marker, or some flag which he needs to carry the information further, whether it is divisible by 2 or not divisible by 2. That information he wants to carry further. So he needed two symbols. He used 0 and 2. He could have used 1, 2, or 5, 6, or X, Y, anything. Now, coming back to shunya, when we say shunya, there are three things associated with it. From when we say the India's contribution is 0. So 0 as the word 0, how we write it, the grapheme, then what is the meaning of it? That it means nothing. That is another part of it. And the third is, it's a position, place value system that comes because of this 0. That once you have this place position and you put 0 here because you want to talk about the place value system. So there are three concepts that are actually related with this concept 0. One is its representation. So when say people say that, well, we find a proof for 0, that symbol is there. So that symbol is one thing. Its meaning is another thing. Okay. And the third part is the place value system itself. Just by having this symbol or the meaning does not mean you get a place value system. That is a totally different concept. And all these three are contributed by India. The symbol, the meaning, as well as the place value system. This is what I understand when they say India has contributed 0. These are the three things which come to my mind. Okay.
I think that's the Shlesha. India contributed 0.
Yes.
Two ways.
India contributed nothing.
But in fact, very much. But
Yes.
also very interesting that an ancient synonym of shunya is purna.
Yes.
So
this Purnamadah Purnamidam Purnat Purnamudachyate Purnasya Purnamadaya Purnamevavashishyate. Here, whether this Purna is 0 or infinity, you can interpret it in both ways. Purnamadaha Purnamidam Purnat Purnam Udachyate. If you subtract Purna from Purna, you get Purna. Now infinity minus infinity is infinity. Purnasya Purnam Adaya. And Purna 0 minus 0 is 0. 0 plus 0 is 0. Infinity plus infinity is infinity.
It is true that it applies better for 0 because infinity subtracted from infinity could give something finite. It's not entirely satisfactory.
It may give finite. Yes, I do agree with you. Yeah.
In the same vein, if I may point out something again, I pointed out in another paper, I think, the notion of infinity in two directions seems to appear only with the Dingot-Bavin episodes. Because in the Dingot-Bavin, when Siva comes in the form of Linga of fire, it's infinite in both directions, positive and negative. And it seems that it appears about the same time as when Brahmagupta is introducing the mathematical concept.
Yeah. Yes.
Anadi and
Anadi Ananta.
and Ananta.
No end and no beginning. Anadi Ananta.
Okay, so there are still a few minutes left, but don't hesitate to ask any questions or not even general. If there's something about the previous lectures which could not be asked, or if you want to remark something on your own work on computational linguistics for German, for instance.
Yeah, I think this is something which maybe.
Maybe please.
See, this is the book which I mentioned last time, which I have authored, where the concepts from Indian grammatical tradition.
And I studied the book. It's very good original contribution also to the history of thinking, means the history of ideas in India, and several questions are raised how they understood the way language is working, like how do we understand the sentence. So it's
Yes.
What about the historical development of the graphical representation for chandas? Graphic representation where you have danda.
Yes.
Or lagu.
Yeah.
And some kind of famous word.
So,
this. What is this?
I'm not sure about it. I have seen two types of one, the avagraha and this, and danda, and horizontal line and like moon, like half moon. That is a Western one. Then this I do not know how long it is, but in school we were taught with the half moon, not with the avagraha. And avagraha I found only in Sanskrit books, the danda and avagraha. I don't think so. In Piṅgala, well,
it's very oral.
Yeah, it's all oral.
You can imagine that works in an oral way.
Yeah. Just gala and that's it. Yeah.
There are also social symbols in Tamil music. So, for instance, there is a circle denotes two strokes, and there is one stroke with a number denotes 4 strokes or 3 strokes, and there's a notation for the pluta and stuff. So if you look at Carnatic music, any textbook on Carnatic music to explain that. But I don't know how well it is. There is a Kudumyale inscription, which is probably from the 8th century. So it's a stone inscription where there are Tara exercises, and then there is a notation for the Tara, which corresponds, of course, to that. But they have more than just 1 and 2. There are notation for.
Yeah, and there will be half, 1/3, 1/4. If it is Tala, then it will be much more complicated.
Right.
Yeah. Yes, yes. Oh, good question. So Lagu and Guru, Lagu is short and Guru is long, heavy. So naturally Lagu should be 0 and Guru should be 1, whereas I'm using 1, 0. Very interesting question. Good, very interesting observation. Well, so what I noticed was in all these prastaras, here if we look at, they start with all G's. So I had to start with all zeros. We cannot start with all ones and then this is how I replace G with 0.
0 looks more heavy and the 1 is very slim. So light. So it's arbitrary in one way. You could do it exactly the other way.
Yeah.
It's just
Well, these are
two
just
values.
simples. These are just simples. Yeah. But because I wanted to compare it with Boolean notation and we have this 0 and 1. So these are just two symbols, G and L. And why they started with all G's? They could have started with all L's and then gone to G's, but okay. So these are just two arbitrary things you can go in any way. Okay.
Similarly, in modern engineering, of course, it could be Boolean. Changing the Boolean notation.
Huh.
Yes. Also in modern
I didn't go. GL is 0, 1.
Yeah. So what I meant there is that's just one of them is legal.
Oh, okay. Yeah, fine. Yeah.
It's just to say, yeah,
Yeah.
it's a pure convention.
Yeah, it's right. Yeah, it's the convention. And actually, Pāṇini could not use lg. Gla is easy to pronounce than lg. G and l, he wanted to make a Piṅgala. I always have Pāṇini in mind. So this two G and L together, if you want to pronounce, you can pronounce G followed by L very comfortably, but L followed by G. Huh?
Like Piṅgala.
Yeah, right. Like Piṅgala. We can't have Pillaga. Piṅgala, Gala. Yes. Gala is natural. So he started with G. Maybe that might be the. But these are arbitrary. But if I want to show the equivalence, then I need to replace G by 0. Then only I can show the equivalence.
India had a hugely developed mathematics, but they didn't develop it either positively nor negatively by constructing an atomic bomb, nor positively by making computers. But mathematics is there, mathematical insights are there.
Yeah, we had insight. Somehow this particular part was totally left unnoticed by the contemporaries. It was very late this was discovered.
Question in your conclusions, I was interested in your suggestion that maybe there was more teaching. That is what.
Yeah, this is what I thought. Yeah.
But I guess the sutras are better for so I imagine that somebody, teacher explained afterwards, I guess it's much easier to remember.
No, recursion definitely is good for memorization, But in order to, if you are asked to write down the spread for these 5 bits, then starting with 1, then writing 2, then 3, 4, this is something which is very tedious. You would directly like to go for the 5th one. So this is one thing. And see, this recursion actually is I find, as a teacher, I found it very difficult to teach this recursion. Students don't understand it, but if I tell them the iterative procedure, they will do it. They will solve the things, but only those who have that kind of ability can understand that recursion. Everybody cannot.
So you need a stack.
Yes.
So you need more.
Yeah. Right.
more
That.
instead.
Right. That is another thing. Yeah. Yes. Yeah. Let me show you some recursion in Pāṇini.
Pāṇini?
Pāṇini.
Really Pāṇini.
Yes, really Pāṇini.
The grammarian Pāṇini.
Not this. This is not good. Let me see.
Then add again a new suffix and again a new suffix.
Yes. Yeah.
Slowly.
So this is, I like this diagram very much. How you can generate infinitely many words, starting from the dhatu patha and the shabdakosh. So dhatu patha is list of verbs. Just a minute. I think I need to share my screen. Can you see my screen?
Not yet.
No. So there was.
Like Sanskrit,
Okay.
German also has huge compounding.
You need to give me permission to yeah. No, not record.
No, but I have
No,
already
sorry.
taken-
Sorry.
You have
Sorry.
to first
No,
copy
I no, by mistake I pressed on record. Okay. So you can see this?
Yes.
Okay. Okay. So you have the dhatu patha, which is a list of verbs. So you start with a verb, add verbal suffix to it, and you get a finite verbal form. If you start with the nominal stems, which is called a pratipadikam, to add a nominal suffix to it, and you get a nominal form. So these 2 green forms, these are the finite forms. Now you can generate these nominal forms from verbal forms by adding certain type of suffixes. So you have the verbal roots, add these suffixes, you get new nominal stems, and you get the nominal forms. Now these nominal stems,
Like do plus doer.
yeah,
Means we could make it.
yeah, fine, yeah. So something like do plus ing doing, or do plus are doer, and then you can have doers plural form, etc. Then to these verbal forms, we can add several prefixes like enter, re-enter. So similarly here we will have, and how many these prefixes? Up to 5 prefixes we can add. And we get new verbal roots. Then there are certain suffixes like the causative, to make something a causative, typically in English, we use make or get or do. Make him bring it. So make, bring. In Sanskrit, there is a suffix which is added to the verbal root, and you get a new verb. Bhu, bhava, bhavaya, kru, karaya, etc. So you get these new verbal roots. But what is interesting is when you have these nominal stems which are derived from the verb or otherwise, to these we can add some suffixes to make it a verb. And to this verb again we can add this suffix to get a new nominal stem, and you go in loop. You can derive several new words, new stems. There is similarly this suffix tadhita, and we have here new nominal stems derived by adding these suffixes, like lazy, laziness. Okay, ness is added, you get laziness, or humanity. So some of these suffixes produce new nouns, and from the nominal forms also, you can add certain suffixes and get and so on. So there is a lot of recursion involved here. Of course, well, here is an example. One example is samabhi vyahara, sam abhi vi ang. These are all prefixes, upasargas, preverbs. These are added to a verb re. You get a new verb. To this niche is added. So niche is from this. You get again a new verb. And to this, ang is added to get a new nominal stem. And to this, nominal suffix is added to get the final word. Okay. Then there is another one, susammodayantika, where su, sam, mud. Su and sam, these are the prefixes. Mud is the verbal root. To this one sanadi suffix is added. To this one krut suffix shatru is added. To this sup suffix is added. You get this. To this again another kan suffix is, it's this kan suffix is added, and then sup, and then finally you get susammodayantika. So it's lot of recursion is there, but of course in practice we don't use this much recursion.
Sometimes in the it even allows some suffixes to come behind the verb, like this we would expect, like let's say Pāṇini, Jayante Taram. May she, or she should be victorious, very excessively. You can put Tara behind the verb.
Yes. Yeah. That I have not shown here. Yes, that is a special construction which is missing here. Thank you. Yeah, of course, that I have not shown here. We can have, you can combine two. Yes. Yeah, that's true. You can go on adding the nominal stems, joining them together to make a very long compound. And I have seen one passage with, one word running 3 pages of the book. This was one long compound which ran 3 pages of a book. Of course, it was in a specific technical language of Navya Nyaya, but such constructions are possible because of this recursion.
There's one interesting aspect to this nominal style. That is, in the nominal style, when you make many compounds, as a sentence. Means to explain the compound, you can put again a sentence.
Yeah. Vigraha Vakya.
So in fact, it becomes almost like a statement.
Yeah.
And the remarkable thing is that if you take Chinese, you have also many words without ending because it's
Right.
not
Yeah.
language. So
Yeah.
there is one book from 1955 where someone compared the nominal style of Sanskrit with Chinese.
I see.
the syntactic.
Okay.
I think that is something that
Oh,
developed
this
by
is-
someone who knows both Chinese and Sanskrit. It could be very interesting syntactic comparison.
Okay,
Like
this
the
is-
same way of expressing can be done in Chinese, and you have a simple Chinese sentence, and you can take a nominal compound or a nominal.
this is very interesting because
Peter Hartmann, 1955.
Okay.
Wissenschaftliche Sanskrit. It's in German.
oh,
So
then it is difficult for me. But no, but this actually interests me because at present we are working on analyzing compounds, which is a very challenging job because there are no suffixes. Just from the position and the context, the words in the context, we need to understand what is the relation of one word with the other. And it's really challenging. And if Chinese processing NLP can help us, then I would definitely be very, very much interested in looking at it. Good, thank you for this. But since it is in German, I will have to find out some German knowing person who can help me in understanding that. Yeah, I can do the good, but then I will have to type in because
Peter Hartmann wrote, he was also in English. In 1955, he wrote Stil des wissenschaftlichen Sanskrit. Later on, he became he's known also as a linguist in the 60s, 70s. Like he maybe forgotten, maybe now. Sometimes he was very influential. So I have to do, I can make a scan for you. What is the longest German compound that is normally used? You have the Deutsche Austauschdienst. That is not so long. That is just 2 elements. Yeah, that's 10 words. It's quite some stations or some sort of even more than elements. That's also, I have some examples for those. German, yes, exactly.
That's a bit more general question, but for the linguists, one of the definitions for the content is better understanding. For instance, main differences of the
yeah.
When you say something,
In French, we were taught in school that the vocabulary is finite and that the longest word is anticonstitutionnellement.
when we were given English, and this is the
So here is one compound with 10 components, and this compound is from the Panchatantra, which is a very popular book among the children. This is from Sanskrit, and yeah, it is Pravara Mukuta Mani Marichi Manjari Chaya Charchita Charana Yugulam. But there is another variant. This has only 9. You can have Pravara Mukuta, Pravara Nrupa is there. I think it's here somewhere. Yeah. Pravara Nrupa Mukuta Mani Marichi Manjiri Charan Chaya Charchita Charana Yugula. And what is the meaning of this? We can see the meaning. Excellent crown, gem, radiant cluster, heap, cover, food, pair. These are the words. Now try to make a sentence out of it. The one whose feet are covered by the heap of a cluster of radiance from the gem of the excellent crown. Excellent crown, gem of the excellent crown. Cluster radiant, cluster of radiance. Okay, heap of a cluster of radiance. Covered by feet. A person whose feet are covered by the heap of a cluster of radiance. So this will be its constituency analysis. And
in order to understand it, you have to figure that it is thinking of the king.
yeah.
And the king is surrounded
Huh.
by certain things.
Yeah.
And on their
all those yeah.
You have the light that illuminates the
feet of the king who is sitting. Yeah, thank you very much. Yeah, yes, yes. Huh?
No. There is more economic
Yeah.
Okay, so let's see what's on. Not a good that is the use of but in as a negation, but then in a sense of it's not a good, like say ashabda, that is shabda, ashabda is not a good word or something. You can use and this and exactly are the same. And function is also similar. To say unmensch, like it's not, it's in fact it's a mensch, but he's behaving very well. Okay, so I think that was very brilliant and stimulating. Thank you very much.
Thank you.
Anugrahita Smaha. We are
happy.
Very grateful to your contribution to our seminar. And to our lectures. So thanks so much, and we hope we will keep in touch, and we will think of future projects. Maybe, who knows?
Yeah.
Especially we should see the cross links with computational linguistics in other languages, and there is much going on nowadays. What is it? Numeric, digital humanities.
Digital humanities.
and in French? Humanité numérique. Humanité numérique. So, yeah, in this sense,
Humanity is mankind.
humanité. So, okay, so thank you for pointing out this again. So, so there is enough scope for progress and for development, and we thank you very much for your stimulating contributions.
Thank you. Thank you very much. And thank you all those who are there online, professors. Namaste. It was nice meeting all of you. Thank you.
For your contributions, your active contributions, and your questions. So we will conclude now, but we will think of how to continue. This we had also a course for mathematics earlier this year, and for today we will say goodbye until soon.
You need to.
I'm telling all type of things, and you are not listening. Professor Amba has muted. So we thank Professor Amba Kulkarni. We should go forward. We will think of it is a little bit innovative, so there are no existing paths. So we have to think of new ways of cooperating, of creating projects and making cooperations between unexpected languages and applications of digital humanities, humanité numérique. So we conclude here, and that conclusion is only temporary, means we want to continue in the near future in one way or the other. Thank you very much. Merci beaucoup. And I will conclude here the Zoom meeting also. Thank you.